Okay, so welcome to the tour of our artifact. This is for the abstract alloy instances. And the projects that you see here, that's basically the workspace of alloy. And we have added 2 additional projects, but we have also changed the code in some of the existing alloy projects, for example, for the visualizer. So the first project that is new is this apps inst, which is for the abstract instances. And that's where most of the work is implemented. Then there's also this evaluation project here, which has some scripts, and you can create the binaries to run everything. But yeah, let's have a look at the project. So if we have a look at the here somewhere at the algorithms, then I'll just show where they can be found. So here we have this algorithm 1, computation of an abstract instance. This all happens in the new package here in the minimizer. And there is a method called minimize. This basically gets the parsed alloy module and the command that we want to analyze. It also gets optionally an instance, a concrete instance that we want to minimize. Then the options of alloy, this has defined stuff like the SAT solver and the verbosity of outputs, and then what kind of upper bound we want to use for the computation. So as we could see, there's the no upper, the instance, then the instance or no upper, and then the exact. Exact is the default, and that's also the one that allows us to compute maximal abstract instances. So yeah, we still check, we still analyze the command once to get the scopes computed that we can then use to initialize the bounds. So this initializes both the upper and lower bounds and creates these signatures templates for these signatures that we show here. So these lone signatures, that's in the bounds initialization. And they basically give us what will this upper bound be look like. That's also computed there. So this is not so trivial. So that's what we get from the alloy reporter. It tells us what are the scopes for every single signature. So this already takes care of inheritance. And then we just implement it accordingly. That's in the init bounds. Then we have this sanity checking that we explained during the somewhere in the threads to validity. And then we run the minimization. Yeah, so this min lower upper, this then starts minimizing or maximizing the bounds. That is, yeah, shown here. We first minimize the lower bound, then we maximize the upper bound. Here, yeah, we do a we have this instance of the delta debugging, and we tell it that right now we are minimizing the upper one first. Okay, so that's a small change in the algorithm. It says first lower then upper, but yeah, it's a while loop that runs while needed, as long as needed. So yeah, it doesn't matter whether you exchange these 2 lines. So in the concrete code, looks like they are exchanged. Then we run a minimize on the upper, which is actually a maximization of the upper bound based on how it is internally represented, so that we can in both cases use the same delta debugging algorithm. And then we run a minimization of the lower. So if we want to have a look at this minimize, that's the abstract implementation. So the really interesting one is actually the check method. So what checks are going to be created. And again, we have the sanity checking, but if we are going for a lower bound, then we create the bound of the candidate and the fixed upper, which we're not changing right now, because while we are minimizing the lower bound, the upper bound stays the same. And otherwise, if we're going for upper bounds, then the lower bound stays the same, and the candidate is the one that we use for, well, in this case, maximization based on how the bounds are constructed. And then, yeah, we actually just run the command. Here we are negating the predicate. So we're basically checking these constraints M with, that's the check now here. We're checking these constraints M with the bounds predicate and the negation of the command predicate. So yeah, we add bounds to the negated command predicate, and this add bounds is, yeah, so this add bounds always creates a predicate that expresses both the lower and upper bounds, no matter which one we're minimizing, because we get both of them as parameters and need to add them as the constraints. So here is an example for the lower bound, which is easier because it's very, very local constraints. So here, if in our bound elements in the lower bound, we have a signature, then we get the lone signature. We just get it from the initialization of the bounds, this thing that represents our atom. And we simply say, well, add this to the lower bound, where we say that this signature has one atom. And yeah, this is already enough to give this constraint that this atom will exist based on the lower bounds. So this, everything happens within this like, expression to bounds to get this bound expression. And the example would be, for example, this one where we say, well, there must be one of this assignment 2, and that's the lone signature that we would have resolved. Here, then for tuples, it's very similar. For tuples, we are also checking whether this tuple actually, whether all the atoms of this tuple actually exist. And if it doesn't, then we ignore the rest of the tuple. If all the atoms that we added to the tuple still exist, then in the end we add it by saying, well, this tuple belongs to the field. And this field, which field it is, that's stored in the bound element that we have collected in the lower bound. So that's this bound representation is also something specific to our kinds of bounds. So they are, as described in the paper, they're different from the alloy ones, and all the implementations are available here. So these bound elements, they have the fields that they belong to or the signature that they belong to, and then the tuple, the atom names, because these are not always directly visible from the elements that it stores, and then in some cases an expression that basically represents this element for the constraint. Okay, so yeah, I think we went over most of the elements of the implementation. There's some additional stuff for the visualization here that takes care of the visualization. Then this implementation of the delta debugging, which is completely generic. We can replace this by any other kind of minimizer and use it for the minimization and maximization. And then the next part that is part of our implementation is here, this evaluation. So that's the evaluation main. This just describes what kind of parameters this thing expects. So first parameter would be always a file, then the mode. So right now there's only the mode first n implemented, but there might be other modes in the future. And then the arguments would be, so this first n is the one used for the evaluation, where we have arguments like how many instances do we want to enumerate, then which one of the commands do we want to use, because some of the alloy files, they have multiple commands, then what upper bound kind do we want to use, and then it also takes the solver as one of the last argument is the solver to use. Some examples, and basically the stuff that we used to run this file in our experiments are in these scripts here. So we all wrap it into this time command to have a timeout. We also capture the memory consumption, timeout here, 10 minutes. And then this is the main command. So that's the jar file that will be built and appear somewhere in target, yeah, that's this jar file. So if you built it using Ant or using BND tools within Eclipse, then you will get this jar file. And then here the file name to run it on, we want the first n. N is 10, so 10 first instances. For command 0, we want exact upper bounds. The solver we use is Minisat JNI. This only works on Linux platforms, so on Windows or other platforms where you don't have the binaries of the Minisat, then which is the ones provided by Alloy, but Alloy doesn't provide them for all platforms. Then you simply use this SAT4J. So you can see how it's resolved. So we call the get solver, and that's basically this constant here. So whenever the name is SAT4J, or if you give a solver that it doesn't understand, which is not one of those, then it just uses SAT4J. Yep, and then we just print this to the memory output, memory log output, and the evaluation also creates as soon as it has computed, because the timeout is external. So as soon as we have computed a file, it's going to print as the output problem sizes, number of concrete instances, and things like that. So we can have a look at an example. The results are here. We ran them in 2 identical computers in parallel. This is the memory log where we can see how many timed out. So for the timeout ones, what we get is somewhere it will write, I think something with code. Yeah. So the command exited with non-zero status 124. This means that it exited. Then we can see which command it was here. So it was this call to the faulty farmer. We don't know from this log, we can't see on which instance it failed, but we can see which instance it failed on, because for every instance that it completed, we basically get some output here that you can expect. So you have to, open these, and then you see what was the command called. So what were all the parameters? Then the current computation that is stored in this. So every computation result is in one CSV file. So here in this CSV file, we have an abstract instance computation for the 8th instance of the stable ring lead protocol. This instance, to compute this abstract instance, it took something like 5 seconds. The size of the abstract instance is 6. And here are the bounds printed. So there are some tuples here in the lower bound, 1 tuple, 2 tuples, and so on. And then the upper bounds constrains some of the elements here. And we see statistics for each of the solver runs. So here you see different numbers of clauses, and this is a really long line. So whenever it starts with primary variables, then it has the primary variables and the clauses. They are maybe the interesting statistics generated from Alloy's SAT-solver calls. So you see that there are some changes. So there's quite a lot of solver calls. So all this is exported as statistics, and then we analyze this in the evaluation that we show inside the paper, where we of course then couldn't report everything, but we focused on the 3 or 4 research questions that we described here. So now if we want to simply build the project, this is all the infrastructure of Alloy tools, so we didn't really do much there. You can just build this. There's a Gradle wrapper, and then we can say build. I would suggest to simply do to ignore the tests for building, because the tests will take a very long time. There are actually some tests which even have an ignore flag because they take even longer. So if you want to really have a look at those, then they are in the abstract instance minimization. For example, the smoke test here, this ignore tag means it's not running it. If you would remove this ignore tag, then you can run basically on all files, let's say of the book, on all files of the example, and this will take some time because, yeah, it will run on all files and try to do lots of computation. Okay, so yeah, we just built it, and the original Alloy tools, it's in the distribution target. So we integrated it simply into the Alloy tools. So now if you just run it, Java jar, and then yeah, something like that, then you get the normal Alloy view. Okay, so this is the module from the paper that we had in the example, and we can run the analysis. There's only one command, this check command here, and Alloy finds a counterexample. So far, everything as usual. Then we have the Alloy visualizer, which we extended now. You can select which kind of bound kind you want to use, and whether you want to display it over the instance or independently. Now let's click the abstract button, and then we should see an abstract instance for this instance. And yes, we see a class where this student one is the assistant of, and this assignment here is assigned to that student. And then the student is grading this, this assignment, while it is also assigned to that student, which is what shouldn't happen in this case. Now, if we click new, then we get a different instance, the way Alloy iterates instances. So far we're abstracting individual instances, and here we see it's a very, very similar reason because the abstract instance shows us what's going on in this case. Now let's see if we can change the options, maybe for no upper bound, and then we could see whether we still get whether we are still able to abstract. Yes, we're still able to abstract. The upper bound in many of these cases is empty, so that means no matter how we extend this with available atoms, the abstract instance property is still valid. We can also have the independent display, and then we only see the part that is relevant for this abstract instance, because the over instance, maybe it makes more sense if you have the instance or none as upper bound types, but that's something to evaluate in a user study.